I think I sent you an email about the new homework assignment at our website. This is on section 6.1, and there are 26 problems in it.
Well, how many?
But, okay, so before you think that it's a lot of work, most of the problems in WebAssign that I assigned, these are like, you don't have to do any, most of the time you don't have to do any work. You just look at the answers and pick the right one. For example, it says f is a one-to-one function if you have 4 choices, and you have to put the correct choice. So most of the problems are really easy. They are not requiring you to go over calculations. Some of them are, but most of them are not. So don't think that 26 is a lot of work. Okay. No, it's due on Monday. It's due on Monday. You have time. You can do 5 or 10 at a time and finish it by then. All right. So what we want to start today is the next section in chapter 6, and this is on the logarithm. The logarithm function, and more specifically, I should say it's the natural logarithm function, but I won't write it down. But it's the natural logarithm function. I bet all of you have seen the log function, the exponential function in pre-calculus. And if you have taken calculus in high school, you might have seen it there as well. However, to truly appreciate how this function is developed in a rigorous way, I will suggest that you delete your memory of the log and the exponential function from before. Okay, so just delete it for the next 50 minutes. Okay. And see how it is defined and how it is developed and how we can come up with the graphs and so on. So the definition of this function is very easy. So let's see how we define this function. We are going to use the symbol ln, not log. Again, depending on what tradition you came from in math, you will use log for the natural log. You might use ln if you're coming from another tradition. So people in analysis, they use ln usually. People in number theory, some other places, they use log for the same function. Okay, but in any case, I'm going to use ln just because it's tradition in calculus to use ln. So what is ln of x? Now usually it is more appropriate to write parentheses around x, because usually when we write a function, we write f of x, right? Usually we should be writing ln of x with the parenthesis around x. However, tradition dictates that I don't use any parentheses. Okay, usually people don't write parentheses around x unless there is a need for it. So if I write x plus 1, then I need to put parentheses around x plus 1. In any case, so what's the definition of this? Well, the definition is that the value of ln at x is the integral from 1 up to x of the function 1 over t dt, and we are defining ln x only for positive x. Only for positive x. So this function is defined only for positive x. Is everybody clear? Now let's see what's the meaning of this function. What is it really computing? Okay, what is it really computing? So let's see. We know this because we understand integration very well now. So let's say I have my favorite x-axis and y-axis, and I'm going to take the horizontal axis to denote t. The vertical axis will denote y, and I am going to sketch the graph of y equals to 1 over t. That is, I'm sketching the graph of the integrand. So what's the graph of the integrand? The graph of the integrand is something like this. If I can draw it nicely. Is that looking good enough? I'll say good enough. Alright, so let's say, so that's the graph of the function 1 over t, and I am going to pick a point here. Let's say, let me pick this point here, and that point will be the point corresponding to 1. So here I have 1. What's the height of the graph at 1? 1 over 1, which is 1. Okay, so I have the graph of 1 over t, and now notice that I am integrating 1 over t from 1 to x. So let's take x to be bigger than 1. If x is bigger than 1, let's say here, so let's say this is where x is. If x is bigger than 1, then the integral from 1 to x of 1 over t dt represents what? It represents the area of the region below the graph of the integrand above the interval from 1 to x. So this is the value of ln of x, right? The ln of x gives me the area below the graph of 1 over t above the interval from 1 to x if x is bigger than 1. Okay? But my definition was for any x larger than 0. So what if x is larger than 0 but it is less than 1? Let's look at that case as well. So now let's assume that x is less than 1. So let me, what should I do? Let me change that. And great. Okay, so I can change that, and let's say the x is now right here. So x is between 0 and 1 now. So here is x. X is between 0 and 1 now. In that case, what's the value of ln of x? What's the value of ln of x in this case? Well, is it the same as the area here? Well, not quite. Well, what is ln of x here? What is the area? So let me ask you this. What's the area below the graph of 1 over t above the interval from x to 1? If I call that area A, that area A is the integral not from 1 to x, right? From x to 1, 1 over t dt. Area below the graph of 1 over t from the interval from x to 1. And so I could then say that this is equal to negative integral from 1 to x 1 over t dt. But then that is the value of ln of x. So I get negative ln x, right? Am I making sense? So what is ln of x in this case? In this case, ln of x is a negative of the area, right? Ln of x is negative of the area below the graph of 1 over t above the interval from x to 1 in the case x is less than 1. So here x is less than 1, greater than 0. Is everybody okay with that? Everybody's okay? So, what's the conclusion here? Let me write down the conclusion here. The conclusion is that ln x is ln x is positive if x is bigger than 1, and ln x is negative if x is between 0 and 1. You agree with that? Let's look at it again. When x is bigger than 1, it was the area below the graph of 1 over t, above the interval from 1 to x, so I get the positive area. But when x is between 0 and 1, we saw that we got the negative of the area, so then it's negative there. Any questions there? Any questions on what I just said? So we know when ln is negative and when ln is positive. So the graph of ln on the right side of 1 is above the x-axis, and on the left side of 1 it is below the x-axis, right? What else do I know? What is ln of 1? What is ln of 1? Ln of 1 is the integral from 1 to 1, 1 over t dt, and when the upper limit and the lower limit of integration are the same, the integral is what? 0. So that means ln of 1 is 0. Okay? Any questions so far? Any questions at all? Yeah.
So you graphed y equals 1 over 2.
Yes.
So, but isn't natural log of x the natural log of x is integral from 1 to x, 1 over t dt, right? Integral from 1 to x, 1 over t dt. And when x is bigger than 1, right? When x is bigger than 1, let me use a different color. When x is bigger than 1, when x is positive, then we get that the integral from 1 to x gives you the green region, right? The area of the green region is given by the integral. However, when x is negative, then the area below the graph of 1 over t, above the interval from x to 1, then that area is given by the integral from x to 1, not from 1 to x. You always go from the smaller number to the bigger number for the area. So you get this. But this is the negative of ln. This is the negative of ln, because ln goes from 1 to x, not x to 1. So this would be the negative of ln. So ln is actually the negative of the area when x is less than 1. Okay? Is everybody okay with that? All right. So all right. So that's that. What I want to do now is sort of show you how I can estimate the value of the log function. The estimation that we are going to get now is going to be rather a rough estimate, but later on in the course we'll show you how to get more exact approximations for the values of the log function. So here's, let me draw the graph of this function one more time. Okay, so let's try to draw it. Okay, so here once again I have the graph of 1 over t
This is where the t-axis is, this is where the y-axis is. And let's say the number 1 is, let's say, right here. Okay, so let's say I want to find, I want to estimate the value of ln of 5. Okay, so let's say maybe we can say 5 is right here. So ln of 5 would be what? Ln of 5 would be the area below the graph of f, below the graph of 1 over t. So this area here, that's the area, that's the value of the log 5, right? Is everybody okay? Log 5 is the area below 1 over t above the interval from 1 to 5. And I want to estimate that. Now, in order to estimate that, what I'm going to do is I'm going to divide it into segments. So let's pick 2, 3, and 4 like this. So what I have then is one segment here, another segment here, and another segment here. Okay, so this is 2, this is 3, this is 4. And I am going to estimate each segment. Okay, so let's try to estimate each segment. What I'm going to do is I am going to estimate it in this way. I'm going to estimate the first segment by the area of this rectangle. I'm going to estimate the area of the second segment by this rectangle. The third segment will be estimated by this rectangle, and the last one will be estimated by this rectangle. Okay? Now, is it clear that ln 5 would be larger than the total area of these rectangles? ln 5 is the area below the graph above the interval from 1 to 5, which is bigger than the total area of these rectangles. Can someone tell me what's the total area of these rectangles? Well, what's the area of the first rectangle? What's the area of the first rectangle? What's that? The area of the first rectangle is? See, each segment has width 1, right? So the area would be equal to the height of the rectangle. So what's the height of the rectangle? What's the height of the first rectangle? Yeah. Well, the height of that rectangle is the same as the height of the graph at 2. Half. So the height of the graph at 2 is exactly half. So that's the area of the first rectangle. What's the area of the second rectangle? 1/3, because the height of the second rectangle is exactly the height of the graph at 3, which is 1/3. The third rectangle is 1/4. The last one is 1/5. So I can easily find half plus a third plus a fourth plus a fifth. If I add that, I get a lower bound for my log 5 that I'm trying to estimate. Now I am going to estimate this segment in a different way. So I'm not going to estimate them in this way. I am going to estimate them by doing this. So I'm going to take this height and this. Okay, so now I am going to end up with an upper bound. If I look at the total area of the rectangles, red rectangles, I'm going to get an upper bound for log 5. Well, again, what's the area of the first rectangle? Now that I am taking the height of the rectangle to be the height of the curve at the left end point, right? So it is 1 plus half would be the height of the second rectangle. 1/3 would be the height of the third rectangle. 1/4 would be the height of the fourth rectangle, right? So I get an upper bound and a lower. So that's going to give me a estimate for log 5. This is rather a crude estimate of log 5, but this is as good as we can do at this moment. Is everybody okay with that? Now, looking at this, can someone tell me what would be a lower bound for log 6 and what would be an upper bound for log 6? Lower bound would be the same, all the same terms, except that I am going to have 1 over 6 as well. Upper bound would be it's the same with the plus 1/5. Basically, in that case, you're going to divide the interval from 1 to 6 into 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6. Well, you're going to have 5 rectangles instead of 4. And this would be the estimate for ln of 6. And lastly, if I have any positive integer n, do you see a pattern? What would be the lower bound for ln? ln of n. Maybe I should put a parenthesis to make sure n is the number here. So 1/3 plus ... What would be the last number here? 1 over n. And what do you get here? 1 plus half plus ... 1 over n minus 1. So we can estimate ln of n in this way. Everybody's clear? Later in the course, we are going to see how we can come up with much better approximate. In fact, we can come up with we can come up with estimations that are arbitrarily correct. Okay, we're going to see that later. That is, we can achieve an accuracy as good as we want to with those estimates. Now, we have the log function. Can someone tell me, again, the ln x is the integral from 1 to x, 1 over t dt. Can someone tell me what's the derivative? What's the derivative of this function? And you are using what? The FTC1, the fundamental theorem of calculus. FTC1. That's what you're using here to say that the derivative of the integral from 1 to x, 1 over t dt with respect to x, is the integrand evaluated the upper limit x. Right? That's what FTC1 told us. So that's the derivative that I could say. Can someone tell me then, by the way, what's the domain of ln of x? What's the domain of ln of x? 0 to infinity, because we were saying that we are defining it for x bigger than 0. So the domain here from 0 to infinity. Now, can someone tell me where the derivative of ln is positive and where the derivative of ln is negative? Where is it positive and where is it negative? Positive for all x, right? For all x bigger than 0. So I could say that the derivative of ln x, which is 1 over x, is in fact positive for any x larger than 0. So what does it tell you about the increasing, decreasing behavior of this function? So ln x is increasing on what? If the derivative is positive on an interval, then the function is increasing there, right? If the derivative is negative on an interval, then the function is decreasing there. So I can say that ln is increasing where? 0 to infinity. Everywhere. It's an increasing function on its domain, right? It's increasing everywhere. Everybody is clear so far. Everything has been clear so far? Okay, so let's now look at some properties of this function. So we are going to call them laws of the logarithm. So here I'm going to let x, y be real numbers and r be a rational number. I don't know, those of you who didn't take Calc 1 with me, I don't know what notations were used by your instructor, but I use the symbol r to denote the way I wrote it, to denote the collection of real numbers. The symbol q that I have with a vertical line inside the q to denote the collection of rational numbers. So here I'm saying that x, y are real numbers and r is a rational number. And another condition that I want is that x is positive and y is positive. So x, y are positive real numbers, and r is any rational number. So here are the laws. What is ln of x times y? That would be ln of x plus ln of y. Property number 2. What is ln of x divided by y? That would be ln of x minus ln of y. 3. What would be ln of x to the power r? That would be the same as r times ln of x. Okay? So r is the exponent on x on the left hand side, and then we can rewrite that as r times ln of x. So these are 3 properties of the log function. And I am going to go ahead and I'm not going to ask you to prove any of these laws in any exam or quizzes or homework, but it is good to go over the proof of at least a few of them to sort of understand how, to better understand the functions, okay? Here is the proof of 1. Here is the proof of 1. So usually I don't give too many proofs, but there are some of them that I'm going to do because I think understanding those proofs gives you a better understanding of the concepts. So I want to prove law number 1. So in order to do that, I am going to do the following. We will show ln of a times x is equal to ln of x plus ln of a. Is that the same as law number 1? Is that the same as law number 1? Here I'm assuming that a is positive. Is that the same as law number 1? Well, you bet. I mean, the law number 1 is ln of xy is ln x plus ln of y for any x and y positive. And if I show that for this, it's the same thing, right? All I did is instead of writing y, I'm writing a. And I'm going to tell you in a bit why I'm using a. Okay? All right, so let's think about the following. What's the derivative with respect to x of ln of ax? Can someone tell me what that derivative is? Do I have to use chain rule? What I have here is ax here, right? Not just x. So if ax were just x, what's the derivative?
1 over x, right? If ax were just x, then the derivative would be 1 over ax. But ax is not x, so I have to multiply by the derivative of ax, which is a, but that reduces to x. But however, isn't that just the derivative? Isn't that the derivative of ln of x? Right? Now, the point is, the derivative of ln x and the derivative of ln ax are the same, right? The derivative of ln of x is the same as the derivative of ln ax, which tells you ln ax and ln x are antiderivatives of what? They are both antiderivatives of 1 over x, right? So since, very good, so since ln ax and ln x are antiderivatives of 1 over x, we get what? 2 antiderivatives of the same function differ only by a constant, right? So now I know that ln of ax is the same as ln of x plus some constant c for some constant c. Can someone tell me what c is? How can I find the value of c? How can I find the value of c? 30 seconds. If you answer that, 2 points. Yeah. What's that? No, yeah? Why is that the case? Why is it ln of a? Well, because we are trying to show that. That's one answer, but how are you getting there? Okay, you don't get the full points. 1 point, okay, 1 point. Who's gonna get another point? What's the correct reasoning to say that c is exactly ln of a? Remember in Calc 1, when you talked about antiderivatives, you were given the second derivative of a function and you were asked to find the function f. What did you do? You integrated. When you integrated, you come up with the c, you evaluate c, and then you again integrate, come up with another constant c, again evaluate c, right, to come up with the f. What did you do to find c? To find c, you plugged in something for x, right? What should I plug in for x to get c? Now, what should I plug in for x in order to evaluate c? What's a suitable value of x that I can plug in and find c? 1. Very good. So if I plug in x equals to 1, so plug in, so let me write that again. If I plug in x equals to 1, then the left hand side is basically ln of a, and the right hand side is ln of 1 plus c, but ln of 1 is 0, so I get 0 plus c, which is c, which tells me that c has to be ln of a. So since c has to be ln of a, I now know that ln ax is equal to ln x plus ln a. And we are done. Well, not yet, I guess. Ln of ax is the same as ln of x plus ln of a. Is that the same as law number 1? Law number 1, I wrote ln of xy is equal to ln x plus ln of y. How am I going to get there? Well, replace a by y. Now you might say, why the heck did you even use a? Why didn't you just use y from the beginning? Well, my answer is completely psychological reason. The moment I try to take the derivative of
ln of xy, people are thinking about y as a variable. Am I taking the derivative of a function of two variables, x and y? But when I write ax, psychologically you're thinking that you have a constant a times x. I'm just taking the derivative of that function. There are no two variables floating around. Am I making sense? So usually in our mind we think of y as a variable and so on. So that sometimes confuses people. So that's why I'm using a. Okay. If I use a, when I took the derivative of ax, you said it was a, but if I had a y there, you might have been confused by looking at it. But again, I could have used y just the same way I used a. It's just that usually people are used to thinking about y as a variable, and that might complicate the process of taking the derivative. In any case, they are the same. So 1 and this thing are the same, so we are D-O-N-E done. Okay. Everybody's okay? All right. How about 2? And this will be the last one that I'll do. How about proving number 2? Number 2, well, remember, is the ln of xy, right? Now, before I do that, first show ln of 1 over y is equal to negative ln of y. We're going to show that first, and then we're going to show ln of x over y. How am I going to show that? Well, let's think about the following. 1 is the same as 1 over y times y, right? So then I know that ln of 1 is the same as ln of 1 over y times y. However, we just proved that ln of x times y is ln x plus ln y. So this would be ln of 1 over y plus the ln of y. Ln of 1 is 0. So then I know that ln of 1 over y would be negative ln of y. Everybody's okay? So basically we are using number 1 in order to prove number 2. Now the general case. So all I showed is that ln of 1 over y is minus ln of y. This is oftentimes, those of you who are in math, oftentimes when we try to prove something, we first prove a special case of it and then prove the general case. So here, this is the special case of number 2 where x is 1. Now we look at the general case. So what is ln of x divided by y? Well, I can say that this is ln of x times 1 over y. Now, law number 1 says this is ln of x plus ln of 1 over y. And now, a few seconds ago, we showed that ln of 1 over y is negative ln of y. And that does it. Okay. Proof of 3 exercise, okay? So you could do it on your own and see how that works out. Everybody's clear? Should I go up there? Okay, let me know if you're done writing it down. Any questions? Any questions at all? I mean, these proofs aren't really that hard. I mean, it's not hard to follow. Okay, so let's now look at some examples before I tell you what the graph of this function is. Let's say I have ln of x squared plus 5 squared multiplied by sine x divided by x cubed plus 1. To be honest, I should be putting parentheses like this around that fraction, right? But I will just succumb to the pressure of tradition, and I'm going to use this. Now, if I ask you to find the derivative of this function, and if you try to use the chain rule directly, and then you're going to apply the quotient rule, right? Well, it becomes messy. If you apply the chain rule first, and then you apply the quotient rule, it becomes messy. So before you take the derivative, you should try to simplify the expression. And what should you do here? Well, this is equal to, we're going to use the log rules to simplify this. What should I apply first? Which law? Apply law number 2. You can write it as x squared plus 5 squared sine x minus ln of the denominator, and then I can use, so this is where I used law number 2, and now I can use what? What should I use? Law number 1. I can say this is, I'm going to view it as the product here. So this is ln of x squared plus 5 to the 2 plus ln sine x minus ln x cubed plus 1. And finally, I can apply law number 3. This 2 that I have the exponent on x squared plus 5, that 2 can be brought in front of the log. So this would be 2 ln of x squared plus 5 plus ln of sine x minus ln of x cubed plus 1. Alright, so now I could go ahead and take the derivative easily. Now, you might say, well, you simplified, but you have more terms. Well, yes, I have more terms, but those terms are much simpler than the expression that I had to begin with. So if I want to take the derivative now, if I take the derivative now of ln of x squared plus 5 squared sine x over x cubed plus 1, then I could take it will be the derivative of the first term. What's the derivative of 2 times x squared plus 5? What's the derivative of this guy? Well, it will be 2. Okay, 2 times. Let's do it one step at a time. I have ln of x squared plus 5. If x squared plus 5 were just x, then the derivative would be 1 over x squared plus 5. But x squared plus 5 isn't x, so I have to multiply by the derivative of that, which is 2x. Okay, plus, what's the derivative of ln of sine x? Again, if sine x were just x, the derivative would be 1 over sine. But then I have to multiply by cosine x. And the last one would be 1 over x cubed plus 1 times 3x squared. You guys agree with that? Well, you might doubt that I misled you. You might think that I can take the derivative of the left-hand side directly by using the chain rule first and then by applying the quotient rule. But you'll see that if you apply the quotient rule, you're going to end up with the expression, but when you try to simplify that, it's going to involve more work. Then now I have almost a simplified answer. All I have to do is write 2 4x over x squared plus 5. Cosine over sine is cotangent 3x squared over x squared plus 1. Not much simplification is required. Is everybody okay? I can well, I don't really want to show you how you can take the derivative of the left hand side by using chain rule and the quotient rule directly. If you want to do it, you could do it at home and see why it is more difficult to work with directly that way. If you want to do it at home. In private, you don't want to do it in public. Okay, but I don't want to do it in public. Okay, but I did do that when I was a student, but at my table, not in front of other people. Okay, so again, the point that I'm trying to make, it's going to take more time to do it. Okay, so this is just easier. So hopefully all that talk is going to make you remember that this is what you want to do if you see log. First apply the log rules and then take the derivative, and that's going to make life a little bit easier. Very quickly, one more example. Here, let's say I have ln A plus half ln B. In the previous problem, I had a log expression, and then I rewrote that expression as a number of log expression, right? I had a log expression. I wrote it in terms of how many were the three log expressions. Here we're going to do the opposite. Sometimes we need to sort of have a multiple log expressions, and then we want to write it as one single log expression. So I want to write it as a single log expression. What should I do? What would be the first step? This is ln A plus what? ln of b to the half, because I can put this as a exponent. And then I have, by applying the law number 1, this is ln of A times b to the half, right? So this is ln of A times root of b, and that's it. Everybody is okay with that? All right. Next time, we are going to see how we can come up with the graph of the log function. Please do not look at the graph of the log function from Google or from the book. We are going to discuss that on Monday, okay?